Hey guys, in today's video we'll go through the material balance of a CSTR reactor, which stands for continuous stirred tank reactor. Unlike the batch reactor, it has an inlet flow and an outlet flow. There's also a couple of assumptions that you need to have in mind when driving the material balance. One is that we're assuming the reactor to be well mixed, meaning that the concentration leaving the reactor is the same at any point inside the reactor, which means that the initial concentration, we're assuming that the initial concentration changes the moment it hits the solution inside the reactor. It is converted to a final concentration, which brings us to the second assumption, which is that accumulation equals zero. In the batch reactor, the concentration change with respect to time. In a CSTR reactor, we're assuming that the moment the initial concentration hits the solution, it changes right away. Therefore, the concentration does not change with time. Therefore, we're assuming it to be in steady state and the accumulation to be zero, which makes it much easier that you won't have to be dealing with integrations or derivative in the material balance. So let's go ahead and start our material balance or mole balance. Alright. So as always, input minus output plus generation equals accumulation. The accumulation term is assumed to be zero because of steady state. There's no change in concentration with time. For our input, that will be moles flowing in, the initial moles flowing into the reactor, minus the moles leaving, plus generation, which is the same as the batch reactor, which is rate of reaction times volume. It hasn't changed, equals zero. Now the rate of reaction, just as we mentioned in the batch reactor videos, could be given in first order, and it can also be given second order in terms of second order. The reason behind the negative here is because the rate of reaction of A is a reactant, it's being consumed, that's why it's negative. If the rate of reaction was in terms of B, the rate of the sign would be a positive because B is being produced. If it was in terms of the products, it will be a positive sign. If it was in terms of the reactants, it will be a negative sign. The rate of reaction can also be given in terms of mixed reactants. For the sake of this video, we'll go ahead and use second order rate of reaction. So in most cases, in a CSTR reactor problem, you'll be asked to size the reactor, which basically means find the volume. So let's go ahead and rearrange this equation in terms of V, and we'll sub in our rate of reaction into the equation. So it will be initial moles entering the reactor minus final mole flow rate minus K Ca squared equals accumulation, which is 0, times volume. We'll take this term to the right side, which will be initial mole flow rate minus final mole flow rate equals K Ca squared V. Now we can solve for V. V equals inlet mole minus the the moles leaving over kCa squared. Now there's a small trick. Sometimes the problem statement is not given in terms of mole flow rate, and it's given in terms of concentration. So you'll use this equation here, which comes in handy, which is concentration equals the mole flow rate over the volumetric flow rate, which is given by small v. Therefore, mole flow rate equals the volumetric flow rate times the concentration. Now we can go ahead and sub this for the molar flow rates in our equation, which will give us V equals volume equals initial concentration times the mole flow rate minus final concentration times the mole flow rate over kCa squared. We'll take the mole flow rate as a common factor. Volume will equal mole flow rate times initial concentration minus final concentration over kCa squared. And that way the volume equation is given in terms of concentration. That's it for this video, and see you in the next video.